In today's lesson, we are continuing on with our volume concepts. Today's lesson's about the volume of pyramids, cones, and spheres. So in this lesson, we are going to talk about how to apply Cavalieri's principle to pyramids and cones. And remember, when we talk about Cavalieri's principle, we're talking about oblique versus right 3D objects. We're also going to identify the formulas for the volume of pyramids, cones, and spheres, and we're also going to practice applying those formulas. So looking at the image on the top left of the screen, we are taking a look at a right cone, meaning the tallest point of the cone meets the center of the base of the cone at a right angle. This is a right cone. And we're looking at an oblique cone. Notice that the tallest point of the cone is not in the center. The center's over here. So imagine that these cones are formed by a bunch of cardboard discs. So these cardboard discs, there are the same amount of discs. So the bottom disc is going to be the same shape and size as the cone on the right. The very top cardboard disc is the exact same area and same height as the disc on the right. So these figures are the same height, and each cross section, each of these cardboard discs is the exact same area. So let's write ourselves a note here. So each cross section has the same area, and the cones are the exact same height. So in our previous lesson, when we talked about Cavalieri's principle, it said that if all of the cross-sectional areas of the figure are the same, and the bases have the same area, they are the same height, we know that those figures have the same volume. So the same concept applies to cones and pyramids. If two figures have the same height and equal area at every single cross section, then they have equal volumes. So looking at this pyramid compared to this cone, the purple cross section is theoretically the same area as the matching cross section on the pyramid. Same with the orange cross sections and the yellow cross sections. Both of the figures are the same height, their cross-sectional areas are the same, they have the same volume. So let's look into the volume of pyramids and cones. So the only difference of pyramids and cones in relation to prisms and cylinders is their volume formulas are a little different. Where instead of it being the area of the base times height, it's 1/3 of the area of the base times height. And just a reminder to us, the capital B in this formula just means area of the base. So the volume of a pyramid, doesn't matter what the base of the pyramid is 1/3 times area of the base times the height. The volume of a cone is the same, 1/3 times the area of the base times the height. And since the base of a cone is a circle, then we can expand out this formula, and it would be 1/3 times pi times the radius squared times the height. So let's look into a couple examples. I'm going to draw a triangular pyramid. So the base of this pyramid is going to be a triangle. So let's see here. So let's give this some dimensions here. Let's say that the height of the pyramid extending from the tallest point of the pyramid down to the base at a right angle is 2 feet. And let's say one side of this pyramid is 3 feet. And the height of the base, and this is going to matter since our base is a triangle, let's say the height of that base is 4 feet. So we can find the volume of this figure. And just a reminder, the volume of a pyramid, no matter what the base is 1/3 times the area of the base times the height. So let's plug in what we know. Volume equals 1/3 times, and so the area of a triangle, the base of this figure, the area of a triangle is half times base times height. So it would be half times 3 times 4, because the base of the base is 3 feet, and the height of that base is 4 feet. And then we're going to multiply by the height of the pyramid, which is 2 feet. So really all this is a bunch of calculations. This is going to be the area of the base is 6. So the area of the base is 6. 1/2 times 3 times 4 is 6 times 2. And so 6 times 2 is 12, and 1/3 of 12 is 4 cubic feet. Let's try with a cone. And I'm going to draw an oblique cone. I want the edge of the cone here. So the right angle where the height meets the base is here. The center of my cone is here. Let's add some dimensions. The height of my cone is going to be 24 inches. And the radius of my cone, the radius of the base, is going to be 9 inches. So using these measurements, we're going to find the volume. And again, the volume of a cone, if we expand out that formula, is 1/3 times pi times the radius squared times the height. And in all of the problems you're going to see today, I'm going to use 3.14 for pi. So when we find the volume, let's substitute in what we know. We have 1/3 times 3.14 times the radius squared, so 9 squared, and multiplied by the height, which is 24. And so when we plug and chug those calculations. We plug them into our calculators. If you're not using a calculator at this point, now would be a fantastic time to do so. And the volume of this oblique cone is 2,034.72 cubic inches. Don't forget inches cubed. All volume is in cubic measurements. All right, into a story problem here. It says that Diani is 1.8 meters tall and wants to be able to stand inside her new tent. Should she buy this tent? So I'm looking at the packaging on this tent. Let me change my pen color here. So the tent features, it is 3.4 cubic meters. Since this is cubic measurement, we can assume that's the volume of the tent. It has a square floor with an 8.4 meter perimeter. Okay, and the height, it looks like it's cut off by the clearance price. So that's a little bit annoying. So that's why Diani can't actually find out if she can stand up in this tent. The height is not given, it's missing. It is unknown in this problem. So in a problem like this where you see just a tent, I recommend drawing it out. So when in doubt, make a diagram. And we know that the floor of this tent is a square. So we're dealing with a square pyramid, or is about as close to a square as I can draw here. Okay. And the last part there. Okay, so this is about the shape of our tent. So let's fill in what we know. We know that the volume of the tent is 3.4 meters cubed. We also know that the perimeter is 8.4 meters. The perimeter of the base of the tent is 8.4 meters, which means each side is going to be that perimeter divided by 4. It's a square floor, so all of the sides should be the same. So each side is going to be 2.1 meters. So length and width are 2.1 meters. And we are missing the height. I'm going to label that in red. So from the tallest point of the pyramid all the way down to the base, we are missing that measurement. So if we know the volume of the tent and we know the dimensions of the base of the tent, we can easily find the height. We can find the missing measurement. So the volume of a pyramid is equal to 1/3 times the area of the base times the height. Let's fill in what we know. We know that the volume is 3.4. We know that the area of the base, the area of a square, is base times height. So it would be 2.1 squared. And then height is unknown. We are going to solve this equation for h. So let's calculate what we know. 1/3 times 2.1 squared is 1.47. And then multiplied by height. So to get h, or height, by itself, we're going to divide both sides of this equation by 1.47. And so the height of the tent is going to be about 2.3 meters. So the height is 2.3 meters in this tent. Let's go back to the original question. It says Diani is 1.8 meters tall, and she wants to be able to stand inside the tent. Should she buy this tent? I think that's reasonable because she's got about half a meter of height left in the ceiling to spare. So she should buy the tent. It is tall enough. Ooh, one of my favorite types of problems. It really speaks to the frugal part of me. A restaurant sells smoothies in two sizes. You've got the orange smoothie, which is the large size, and you've got the purple smoothie, which is the small size. So this problem is asking us which size is a better deal. So we have to find the bargain buy in this situation. And notice how they're not giving you the size of the cup. The restaurant's not telling you, oh, the large is X amount of ounces or X amount of cubic centimeters. So we need to find that information on our own. So let's take a look at these dimensions. I'm looking at the orange smoothie, and it is about 10 centimeters across, and the purple smoothie is about 7 centimeters across. So we could find the radius of the opening of each cup, and we're given the length of the edge of the cup, which is 15 centimeters in the orange smoothie and 12 centimeters in the purple one. This is not the height of the cup. The height of the cup is the measurement from the tallest point, so about here, all the way to the base. We need to know the actual height. So from the tallest point directly to the center of the base. So we need to find the height of each cone, because these glasses are in the shape of cones. Find the height of each cone before we can do anything else. So when I drew the height of each of these cups, notice that the height should form a right angle with the base of the cup, or the opening of the cup. I'm forming a right triangle here. So I'm going to draw my large smoothie right triangle from the height to the outer edge of the cup. And I'm going to fill in what I know. The outer edge, or the hypotenuse of a right triangle, is 15 centimeters. Now, the vertex of this right angle here to the outer edge of the cup, that's actually the radius of the base. So if you take the full width of the circle, that's 10 centimeters, and we cut it in half, we get a 5 centimeter radius. So now the only length that's missing is the height. That's our missing side. So we're going to use the Pythagorean theorem to solve for h, to solve for the height. And just a reminder, Pythagorean theorem says a squared plus b squared equals c squared. A and b are the legs, and c is the hypotenuse. So when we plug in this information to the Pythagorean theorem, we should get h squared plus 5 squared equals 15 squared. So we're going through and we're evaluating each exponent. So h squared equals 200. And so if we take the square root of 200, h, or the height, is approximately, to the nearest tenth, let's say 14.1 centimeters. And that's for the large smoothie. So I'm going to go ahead and label that on my diagram, that the height of that smoothie is 14.1 centimeters. Now let's go to the small smoothie, the purple smoothie. And I have also formed a right triangle with this one. So my height is unknown. The radius of the circle is half of 7, so it's 3.5 centimeters. And the outer edge of the cup is 12 centimeters. That's the hypotenuse. So like before, leg squared plus the other leg squared is equal to the hypotenuse squared. So h squared plus 12.25 is equal to 144. Let's subtract 12.25 from both sides, and h squared equals 131.75. Take the square root of both sides, and h is approximately 11.5 centimeters. The height of the small smoothie is about 11.5 centimeters. All right, from here, now that we have the dimensions of these cones, we are going to find their volume. And just as a reminder, the volume of a cone is 1/3 times pi times the radius squared times height. So, the volume of the large smoothie. I'll write that in orange again. The volume of the large smoothie, using 3.14 for pi, is 1/3 times 3.14 times the radius, which is 5 squared, times the height, 14.1. So, plugging in these numbers into my calculator, I'm getting the volume to be about 368.95 cubic centimeters. For the small smoothie in purple, it's 1/3 times pi, 3.14, times the radius squared, and the radius is 3.5, times the height, which we found to be 11.5. So the volume, when I multiply all of that together, is 147.45 cubic centimeters. Okay. The whole goal of this problem is to find out which size is a better deal. So we need to find the price per cubic centimeter of smoothie. So the price per cubic centimeter. So the price per volume of the large smoothie is going to be the dollar amount, so $5.89, divided by the total volume, 368.95 cubic centimeters. And so we are going to get, we're going to have to round here. This is approximately 0.016 dollars. So less than 2 cents per cubic centimeter. And this is the large smoothie. The price for the small smoothie is going to be the dollar amount, so $3.49, divided by the total volume. And so the price of the small smoothie is approximately, we're rounding again, $0.024 per cubic centimeter. So that's less than 3 cents. So we're asking which size is the better deal? Well, the better deal is going to be whichever one has a lower price per cubic centimeter. And in our case, the better buy is the large smoothie, because it's a little less than 1 cent cheaper per cubic centimeter. So the better deal is the large smoothie. If you've ever seen in grocery stores the price per ounce of cans, of any sort of containers, usually in the bottom left corner of the sale price of an item, it will list the unit price. That's how you're going to be able to tell which brand of food is the better buy. We just took a roundabout way of doing so. So the volume of the sphere is going to be 4/3 times pi r cubed. This formula is a little bit different from what you're used to. So the volume of a sphere, once again, is 4/3 times pi times the radius cubed. It's really important to remember, this is where a lot of errors pop up, we are cubing the radius, which means you're taking the radius and multiplying it by itself 3 times. So let me give you an example. I'll draw the best circle that I can. Not great, but passable. And we are going to make that into a sphere. And here's the center of the sphere. Let's say my radius is 15 feet. Why not? So we are going to find the volume of this sphere. Again, volume is 4/3 times pi times radius cubed, radius to the 3rd power. The only measurement you really need in this sphere to find the volume of it is the radius. So volume equals 4/3 times 3.14 times the radius, which is 15, to the 3rd power. And when you plug all of this into your calculator, the volume that you get is 14,130 cubic feet. So now we've got an example problem. The drama club makes a big ball from foam to hang above the stage for a play. They plan to cover the surface of the ball with metallic fabric. What is the minimum number of square meters of fabric that the club needs? So there's a lot of moving parts to this problem. So we are asking for the minimum number of square meters of fabric. And we are only given the volume of the ball. The volume of that ball, which is a sphere, is 1.8 cubic meters. So in order to find any other measurements like surface area, which will be coming soon, we need to find the radius of this ball. We need to know how wide across this ball is to find out anything else. So the first step in our process, since we are given volume, we need to find the radius of the ball. So the volume of a sphere is 4/3 times pi, and we'll use 3.14 for pi, times the radius cubed. So since we know the volume is 1.8 cubic meters, we're going to replace V with 1.8. And we need to solve this equation for R. From here, 1.8 stays the same. 4/3 times pi, or 4/3 times 3.14, is 4.19. We're going to divide both sides by 4.19. So R cubed is going to be equal to 0.43. We need to take the cube root of both sides of this equation. So R is going to equal the cube root of 0.43. And when I estimate that, I'm going to get 0.75 meters. The radius of this ball is about 3/4 of a meter. But we're not done. We now have a dimension to work with. So we're going to use that dimension, and we need to find the surface area of this ball. We are trying to wrap this ball in metallic fabric. We need to know the surface area so we know how much fabric we need to use. So we need to find surface area of a sphere. And so the surface area of a sphere, the formula for the surface area of a sphere is actually 4 times pi r squared. So the surface area of any sphere is 4 times the area of the center, or the same circle, a circle with the same radius. So we're going to take that formula, surface area equals 4 times pi times our radius, which is 0.75 squared. So when we calculate this, all of this is an estimation. So the surface area is approximately 7.1 meters squared. Surface area is always a square measurement. So that is exactly how much fabric, the minimum of how much fabric needed to cover the ball. So the club needs at least 7.1 square meters of fabric. And there you have it. So a summary of our concepts today, we learned about the volumes of pyramids, cones, and spheres, and how we can use them appropriately. Go ahead and check our teams for more information. If you have any public questions, make sure you are posting in the office hours channel of our team. And if you have any private questions or would like more one-on-one help, please send me an email. Thanks and have a great day.